Hello, everyone. We are Frinn, and we're here to present to you our project on fruit and ripeness identification. Next. The goal of our project is to develop a model that could accurately classify an input fruit image into its specific fruit type and the state of the fruit, either being ripe, unripe, or rotten. We limited ourselves to 5 fruit types. The main idea for this project came from one of our group members complaining about a whole batch of recently bought berries contaminated by one moldy berry. We thought we could scale this idea to a large agricultural level where the goal is to minimize fruit waste by identifying spoiled fruit before it can contaminate others. Next.
So first, we worked on creating a large dataset covering all 15 classes. So we used an online dataset for 6 out of the 15 and collected the remaining images through screenshotting and data augmentation, as well as taking photos from our own fridges for testing. To augment the data, each online image was run through the 9 transformations shown on the right. And we specifically chose these as fruits are identical in any orientation and avoided transforms that alter color, since color has meaning in our data. Next. So here's a quick example applying some transforms and showing what our input data looks like. Next. Next slide, please. Sorry. So at this point, our dataset had around 27,000 images, but there's clearly some imbalance. Next slide. So from there, we balanced the dataset by reducing it to 1,000 per class for a total of 15,000. And this minimizes chances of bias in the data and reduces overall training time. And we used a train validation test split of 64, 16, 20%. Next.
So the architecture of the 2 final models are multi-headed CNN models with transfer learning and without transfer learning. Both models take image input, which goes through a shared convolutional layer. Then they're passed on to 2 different 3-layer NLP heads, where first classifies the fruit type, and then the second classifies the ripeness state. The model without transfer learning has the 2 convolutional layers of our own design, and the transfer learning model uses a pre-trained frozen VGG16 with 1 additional trainable convolutional layer. Both model calculates their loss by summing the loss of each output head. Next. So the table on the left shows the range of hyperparameters, and then the table on the right shows the important hyperparameters that were not mentioned before. We weren't going to too much detail, but we performed a random search to arrive at our final design. Next. So for the sake of time, we'll be mainly focusing on the transfer learning model. The 2 loss plot at the top shows the state and type loss, and then while the bottom shows their overall sum loss. Since we're summing the 2 losses, we wanted to know if the state loss will compete against the type loss. The plot showed they converge instead of competing. Next. The accuracy plots are laid out very similarly as the loss plot. These plots show that the model does not overfit. The transfer learning model is able to reach a higher validation accuracy in a shorter number of epochs as expected. Next. The final accuracy table was created with the balance test that mentioned before. As seen on the table, the transfer learning model outperforms random forest baseline and non-transfer learning, and it's able to reach 99% accuracy. Next. So first, seen by the type confusion matrix, the model works well, but in some cases, it is confused with fruits that has a similar shape or color. And in the state confusion matrix, we'll be mainly focusing on rotten, as the model has a hard time predicting whether something is rotten or not. Additionally, 1 rotten fruit can spoil the bunch. Therefore, it is important to reduce the false negative in this category. Further analysis using recall and precision show that although the model is worse at reducing false positives, it has low enough false negatives to be considered good. Next slide.
Sorry.
Oh, no.
Okay, so for the qualitative results, we will mainly discuss misclassifications and the use of specialized test set rather than correct classification. But first, here are 2 examples of correct classification. Next slide. So the first qualitative result relates to the type prediction, and more specifically to the shape of certain fruits and the inherent green color of unripe fruits in their background. As shown in the confusion matrix, the model will sometimes misclassify apples and oranges. We think this is due to the similar circular shape compared to other fruits. We hypothesize that the model may be learning from the background of the images, for example, with unripe fruits that are usually green on top of a green background. Here are certain misclassification examples that demonstrate the similarity in shape between apples and oranges. Next slide, please. Another qualitative result relates to the state prediction. We believe that the model is sometimes confused when trying to predict the rotten class, as the stages of a fruit rotting are numerous, and additionally, the rotting of some fruits are not as apparent as others. For example, some fruits rot from the inside versus others grow white mold. This could be avoided during the data collection phase by picking photos that are truly rotten and do not resemble the ripe class. We also observed when taking images with our phones in a shady setting, the model incorrectly classifies the fruit as rotten. Next slide, please. Our final qualitative result is more of a check on some hypothesis our team had on the model learning from the background. But with the use of 3 specialized test set, we learned that the background did not affect the prediction of the model. Next slide, please.
So now knowing our models and seeing the results, we can generalize to some key learnings. So our project uses a multi-head CNN with shared convolution layers as opposed to a model with 15 outputs. The distinction is that we're performing 2 separate classifications, but the 2 tasks are very similar and likely share a feature space. It's hard to predict exactly when this approach works, but essentially when solving 2 related problems, you can create a 2-in-1 model by sharing the conv layers to reduce the parameters to optimize. In terms of data, we were concerned the model would bias between images with different backgrounds, and creating specialized test sets was fast and gave us clear proof that this wasn't the case. Also, our model was very sensitive to lighting changes in photos from our phones, again, proving that real-world data is different. Next slide.
That's the end. So one last sentence.
Yeah, so lastly, we thought about some potential changes relating to data, hyperparameter search, and implementing simple solutions.
Okay, great. Thank you. I think I accidentally advanced one of those slides. I apologize, Mark. I might have cut you off, but you ran out of time. One of the issues with this Zoom thing is so I'm missing a little bit of the slide. So when I click something to see the slide, I'm also screwing up your slide. So I apologize. It's a really interesting effort, and you did lots of really interesting things using transfer learning, multi-headed things. It seems like you've got a real good grasp of lots of the things that are going on in this course. There are many things to pick up in this course, and it's only by gaining this experience that you really touch it. I think you've done a good job of that. One quick question I had was just somewhere in here you said when you had the transfer learning model, I'm hunting it up here. Yeah, you added in this additional convolutional layer that
That's trainable.
That's trainable. Is the answer to their question, why did you do that? It was in our hyperparameter search to add and subtract that, and it won?
Yeah, it had a better result.
Yeah, so there's no, that's interesting because normally people don't think about doing that. You kind of assume one of these fancy networks have figured out all the little bits and all you need is.
Oh, it was actually recommended by our TA, Phil.
Oh, really? Oh, there you go, Phil. You get a bronze star for that. That's interesting. But there's no, I guess we don't have an explanation. Oh, maybe Phil has an explanation for why he suggested it.
Yeah, I mean, you want to learn, I guess these networks learn all sorts of general parameters that are useful to classifying a broad array of images. So you want to generate an embedding where you're able to combine all these individual features into a space that's actually specific for fruit. And then from there, you can branch out into MLP.
You're characterizing that extra convolutional layer as creating an embedding based on all the features described by the pre-trained VGG. That's what you're saying. I'm really didn't think of it that way. That's interesting. Actually, we should get back to asking them questions. Did I have anything else? There's a lot to pick up. I got. It would be nice if these. When you have three things on a slide, it's hard to know what to look at and hard to find the title. So you were, here your discussion is about the fact that you have two kinds of classes coming out, right? Mm-hmm. State and type, and then this is the combination of the two. Yep. And your overall loss was the sum of the two losses, or is that right?
Yeah, it was just the sum of the two losses.
Yeah, that's interesting. Some other groups might be interested in that because other groups have diverged and just created, binary classifiers to go after each individual thing. Whereas you never did that, right? You never did separate classifiers for anything. Is that correct?
No.
Oh, we did try to see the result of like a separate classifier, and this actually was on par with that.
It was on par.
So classifying only state and type. Yeah.
Oh, interesting. Other groups are finding different. That's interesting. I don't have any other questions. Do you, Phil?
Yeah, I was just going to comment. I think your use of specialized test set to test a specific hypothesis about your model learning background versus fruit, I thought that was great. You had a specific question in mind, and then you collected the data set to specifically test it. That's awesome. And then from your accuracy, it looks like you solved the fruit ripeness problem. So great job. Time to market it to grocery stores.
Great. All right. Well done.
Thank you.
All right.